The title is Infrared Spectroscopic Study of the Adsorption and Dissociation of alkali halides on Supported Metals by Rasko, Bontovics, and Solimosi, and the paper will be given by Dr. Rasko.
Mr. Chairman, ladies and gentlemen, may I start with the good news? Dr. Idris, your bag has been found. Okay. At the beginning of this infrared work, we have been motivated by two things. First, we have recently started with a catalytic project, aiming the catalytic destruction of these hazardous halogenated organic compounds. I don't want to go into details of these catalytic results. May I mention only here that the thermal decomposition of methyl chloride on supporting palladium starts at about 673 Kelvin. Very interestingly, the addition of water and of a mixture of oxygen and water enhances the amount of methane and hydrochloric acid involved in this reaction. A deeper insight into the surface processes of this catalytic reaction would be of great help in interpreting the catalytic results. The second thing, these alkyl halides, particularly methyl iodide, would be suitable compounds for the generation of adsorbed methyl, which play an important role in many syntheses like methanol synthesis, Fischer-Tropsch synthesis, and even in the oxidative methane coupling. There was a certain personal motivation which was killed by Helmut Metzinger in his lecture. So I have to modify my original sentence. Although there are many papers dealing with adsorbed methyl on single crystal, till to the lecture of Professor Metzinger, nobody saw adsorbed methyl during merely catalytic circumstances. His detection in catalytic circumstances, that means at elevated pressure and supported oxide, should have been a personal challenge for us. Taking into account of the predictable low surface concentration of the surface species, we have used Fourier transform infrared spectrometer, and for avoiding the self-absorption of silica, we subtracted the baseline from the actual adsorption spectrum. We applied a very broad temperature range ranging from 193 up to 673 Kelvin. In this lecture, first I should like to summarize briefly the data concerning the physisorption of methyl chloride on palladium silica, and after that I should like to talk about some results concerning the dissociation of methyl chloride on palladium silica, and in context of that I should like to show some spectra referring the effect of potassium on this process. As a short comparison I should like to take between methyl chloride and methyl iodide adsorption on supported silica, and finally to permit me some conclusions will be drawn. Let me start with the general picture. This transparency shows us the OH, CH stretching and CH deformation region of our spectra. The spectrum number 1 obtained by us for gas phase methyl chloride, which is identical with the literature data. If methyl chloride was adsorbed on supported palladium spectrum number 2, a new band in the CH stretching region at 2962 appeared, and in the CH deformation region we have observed a small shift with comparison of the spectra with the spectra of gaseous metal chloride. These new bands and these shifts could be regarded as signs for physics of metal chloride. More dramatic change occurred in the OH region of the sample. I will turn to this region in a minute. When the gas phase was removed at the same temperature, I mean at the temperature of the adsorption, a very small band at 2954 wave number remained on the spectra, and this big broad absorption in the OH region has been removed. I will deal with this in a few minutes too. Okay. After the pretreatment applied in our experiment, a sharp and intense band at 3744 wave number remained on the spectrum, which is characteristic for silanol, SiOH, on the silica. When methyl chloride was added to this sample at low temperature, the intensity of this band went to the minimum, and a broad absorption at the low wave number side of this band built up, which is characteristic, this one, for hydrogen bridge bonding species. Very interestingly, at the end of our experiment, when this broad absorption has been removed, either by evaporation or any other treatment, the intensity of silanol group hadn't reached its original value. So, we have performed MS mass spectrometric analysis of the gas phase during similar circumstances, and we have found dissolution of methyl chloride and a small amount of hydrochloric acid and methane. The bigger part of the removal of the band characteristic for hydrogen bridge bonding can be interpreted by the dissolution of molecular methyl chloride, but the question arises, what is the cause of the reduction of the silanol band during this process? We proposed here a scheme which can explain why silanol groups has been in a smaller intensity after this adsorption process. This scheme contains a very unusual step, namely that a proton of a silanol group can interact with the methyl group from the methyl chloride. This is only a proposal, this will be discussed. A different kind of experiments were performed as follows. After adsorption of methyl chloride on palladium silica catalyst, the gas phase was evacuated. The band at 2954 centimeters remained only on the spectrum. This band decreased with the increase of temperature noted here, and at a given temperature completely disappeared from the spectrum. Very surprisingly, however, at this temperature, the bands in the CH region reappeared. A dominant band at 29, 20 wave numbers appeared as a new band. We believe that this band belongs to the adsorbed surface material. This band can be detected up to considerably high temperature. In this case, we detected it at 373 Kelvin. Another type of experiment, when our sample was kept in methyl chloride at the temperature indicated here for 10 minutes, and after that the sample was cooled down to the room temperature and the spectra were registered. Naturally, the spectrum of gas phase methyl chloride masked the whole spectra of surface species. That's why we have evacuated the gas phase at room temperature and we obtained the spectra at the right part of this figure. Again, the band at 2920 can be detected up to 473 Kelvin as a sign for the presence of surface methyl group. Similar experiments, as the later transparency showed, were performed on pure silicon. In the absence of palladium, there was no indication for the presence of surface methyl. It should mean that the dissociation of methyl chloride should occur on the metal part, on the palladium itself. In the presence of potassium, the appearance of this, the characteristic for adsorbed methyl appeared at considerably lower temperature here at 203 Kelvin. Oh yeah, this effect can be interpreted on the basis of the classical potassium effect, through that potassium can donate electron to the metal, metal donates further electron to the methyl chloride by weakening the bond between carbon and chloride. Thus, the dissociation of the bond between carbon and chloride would occur easier at low temperature. Let me show you the spectra obtained during the methyl iodide adsorption on the same sample. The main different feature from this spectra is that the band characteristic for surface methyl group appeared at considerably lower temperature than in the case of metal chloride. This can be connected with the bond strength difference between methyl iodide and methyl chloride. And so on. And finally, may I summarize our conclusions here? We strongly believe that surface OH groups are involved in bonding of these alkyl halides on the surface through a hydrogen-rich bonding, and these OH are consumed in a small extent by formation of hydrochloric acid and methane. Both alkyl halides can dissociate on the metal bands, which are characteristic for surface adsorbed methyl group. In the case of methyl chloride, is 29, 20 wave number, and in the case of methyl iodide, 29, 22 wave number. The adsorbed methyl group is detectable up to 473 Kelvin, And as I have shown lately, the dissociation of methyl iodide starts at lower temperature than that of metal chloride, and the extent of its dissociation is higher as the intensity of the band is both higher. And finally, the presence of potassium can promote the dissociation of methyl chloride on supported silicon. Thank you.
You've stressed the interaction very much of the methyl with the surface, but I'm wondering whether you ought not pay a little bit more attention to the interaction of the chlorine atom of the molecule with the surface. First, in respect of the perturbation of the SiOH, and secondly, especially in regard to the effect of the potassium in easing the dissociation of the molecule. It seems to me that you could have a quite strong ionic interaction developing between the Cl of the alkyl halide and the potassium, for instance.
Yes, Professor Stone, you are absolutely right, but I think that due to the appearance of surface material, that means in the case of the methyl chloride, that this temperature was 283 Kelvin. We shouldn't have account the effect of chloride on the surface. At about this temperature, where the dissociation of these alkyl halides occurs, yes, adsorbed chloride, adsorbed halide atom should be on the surface. So it's one of our future plans to investigate the effect of pre-adsorbed chlorine or pre-adsorbed iodine on the whole process. But I can imagine that we would have a profound effect of that.
Janos, you mentioned in your first transparency that methyl chloride physical on your surface. Okay?
Right.
Right. We know that on a single crystal, the difference between adsorption and chemisorption state is very limited. It's about 5 or 10 kilofarad more. What is your opinion? What is the difference in support metal?
Will you have a minute? I will search. Well, probably it could be a great surprise for you, but I should like to show you this picture. This is the integrated absorption of the bands appearing in the OH region, right? It was a minimum of the COH bands intensity at very low temperatures, and at around the same temperature there was a maximum in the broad bands intensity. I guess the physisorption could occur only at very low temperature here, because after this temperature range, the intensity, or more precisely the integrated absorption of the broad absorption decreased, while the intensity of the original COH band increased again. So the physisorption of this methyl chloride is limited only in a very small temperature regime. I guess this temperature regime is that one.
How about the possible some erosive effect of the catalyst metal by the hydrogen chloride, especially at high temperature range?
You mean we should investigate the absorption of hydrogen fluoride?
Or hydrogen chloride evolved, that some erosive effect?
Frankly speaking, I don't know.
And do you think that you can extend of your catalyst system to other more complex hydrogen halogen involving organic compounds for some oxidation of this?
Yes, we are planning and we are doing. as a continuation of this work, the adsorption of several halogen-containing hydrocarbons too. But I had only 20 minutes for lecture.
Yeah, I think this is a very interesting example of surface chemistry. We can see the surface chemistry. The question I had sort of related to the last one. If you went from methyl chloride to ethyl chloride, you'd have a possibility of forming ethylene or something like that, where you would have actually a catalytic system. One of the most frustrating things about infrared studies of catalytic systems is always that what you see are the spectator species at highest intensity. In the system, you see the interaction of the hydroxyl groups changing. I wonder if you wouldn't get some ethylene.
Yeah, Professor Hall, the measurements on ethyl chloride adsorption on the same species has been performed by our coworker Julia Bontovich last week. So the results are brand new. We have been in Budapest last week, so I can't summarize the main results of it, but we are tending to do these experiments further and further, and probably by mass spectrometric analysis, we can detect ethylene formation, like in the case of methyl chloride. So we have brand new experimental results on that.
We know from the literature that methyl chloride it's a very good model compound to investigate the phenomenon of Fermi resonance, both in gas phase and in absorb phase, for example, on aluminum and different zeolites. My question is, could you use this Fermi resonance to interpret your results partially or not?
Well, of course, we should use this Fermi resonance in interpreting of our spectra, but the time is limited. I should like to propose to you to go outside of the auditorium and we will discuss personally this problem.
Thank you very much.
Thank you.